All righty, let's go ahead and get started. So last time we started into thermodynamics and we discussed the different temperature scales that could be used. And we found that in physics for this course and in general in physics, the units we want to use for temperature are Kelvin. And so, of course, since we're not used to using Kelvin in our everyday lives, we want to know how do we get Kelvin from a temperature scale we may be used to. And so what we found was that if you want the Kelvin temperature, you take whatever the Celsius temperature is and you add 273 to that number. And that'll give you Kelvin. And so what this says as a conversion is that Kelvin and Celsius are basically the same thing, except their starting point is different, right? 0 Celsius is not the same as 0 Kelvin. But if I increase by 1 degree Celsius, it is the same as increasing by 1 Kelvin. So the size of a Kelvin is the size of a Celsius degree, but where the temperature scale starts is different. Kelvin starts way down at a very, very low temperature, whereas Celsius starts wherever water freezes. Now, along with that, if you want to know this, we won't make use of this conversion that much, but there is a conversion that says if you want Fahrenheit and you know Celsius, then you can get Fahrenheit from the Celsius temperature by doing this conversion. You take the Celsius temperature, multiply it by this number, 9/5 it happens to be, and you add 32. Now, when you look at this conversion, it's very similar to the previous conversion in that it's whatever Celsius is plus a number. The difference is the term that has Celsius on it is being multiplied by a factor. And so what that tells you, doesn't matter what the factor is, but the fact that it's multiplied by something means that the size of Fahrenheit is different than the size of Celsius. So if you increase by 1 Celsius, you don't increase by 1 Fahrenheit, you actually increase by 9/5 instead. So more than 1. Okay. So those are 2 conversion factors. And of course, just as is true for any equation, even though I wrote these equations like this, where the first one is how to get Kelvin from Celsius and the second is how to get Fahrenheit from Celsius, you could manipulate the equations to get Celsius from Fahrenheit. So if you know the Fahrenheit temperature and you want to get Celsius, you just do the algebra on this equation and solve for C. That's all there is to it. So that was the first big thing we found last time. And of course, Kelvin is the units for physics. The next thing is we started into the big topic, which is called calorimetry. So this is the first main topic in thermodynamics we're going to cover. And this deals with equilibrium temperatures. So you put a whole bunch of different items in a box, and that box is closed off from its surroundings. And each item may be at a different temperature. And you want to know, after a while, the hot things will cool down and the cool things will heat up until such time as they all reach the same equilibrium temperature. And you may want to know, what will that temperature be? That's one of the things calorimetry can do for you. And what we found was that the equation we're going to use for this is Q equals Cm delta T. And here, Q is heat energy. So how much energy or how much heat do you have to apply to this item to change its temperature by whatever delta T will be? C, that's the specific heat. And that basically depends on the material. Are you talking about styrofoam? Are you talking about wood? Are you talking about aluminum? What is the thing you're trying to heat up? Because obviously different materials, if you want to increase their temperature or decrease their temperature, will take different amounts of heat energy to do it. Metal, being a conductor, is really easy to change the temperature. So you don't need to apply as much heat. But wood, or styrofoam especially, takes a heck of a lot of heat to be able to change the temperature of the item. And so specific heat is specific, meaning it depends on what material you're talking about. M is mass. So obviously, if you have a heck of a lot of this material and you want to change it by 10 degrees, that's going to take more energy to do than if you only have a little bit of the material and you want to change it by 10 degrees. So the more mass you have, the more heat it's going to take to change the temperature. And of course, mass is in kilograms, just like in first semester physics. And then delta T, that's change in temperature, which means final temperature minus initial temperature. Okay. So what we're going to do today is, of course, work a bunch of example problems using this equation and see how to actually solve problems. Now, one thing I mentioned last time, which is a trick, it's like a shortcut, is the fact that although the rule in physics is that anytime you deal with temperature, you have to use Kelvin as your units, there is the possibility of using Celsius sometimes. And that is if the equation has delta T instead of just T by itself. So it wants to change in temperature. How much are you changing? You can use Celsius instead of Kelvin. You don't have to. You can always use Kelvin if you wish. But if the equation has delta T in it, it turns out that since Kelvin and Celsius are the same size, delta T for Kelvin is the same as delta T for Celsius. So that's up to you when you're solving the problems. Do you want to use Celsius or Kelvin? All right, so let's do some example problems and see how this works. So we'll do some very simplified versions first and then get into the more realistic types. So the first example, let's say you wish to increase the temperature of 0.5 kilograms of water by 20 degrees Celsius. How much energy should you add? Okay. So there's a basic question. We have some material, water, a certain amount of it, 0.5 kilogram. And we want to change its temperature by a certain amount, 20 degrees Celsius. What am I looking for? The energy. How much energy is required? Well, I know that in order to do this, I'm going to use the equation Q equals Cm delta T. I'm looking for Q. How much energy should I add? I'm given what type of material, so that tells me about the specific heat, the mass, how much of it, and the change in temperature. How much do I want to change its temperature? So one thing we need to know is what is the specific heat of water? And so in general, you could look this up on Google or whatever, but I will tell you specific heat for water is about 4186 joules per kilogram Kelvin. Okay. Now, if you take chemistry, a lot of times they use different units. They'll use calories and grams and things like this. And they may have the specific heat of water as 1. Or if they're using kilograms, then they'll say it's 1,000. But in this class, since we're using joules as our unit of energy, it turns out that the number is different. It's 4186. So that's what we're going to use. It's not something you have to memorize. If you're on a test, then either the question will state the specific heat, or at the beginning of the test, I'll have a list of specific heats that are required. So I'll never ask you to memorize the specific heats or anything like that. You just have to use them. So this is a fairly straightforward question. Let's just plug the numbers in and get our answers. Specific heat, 4186. How much water do we have? Half a kilogram, 0.5. Delta T is final minus initial, but I know the change already is going to be 20. So 20, and it's positive 20, by the way, because I'm increasing the temperature. If I were trying to decrease the temperature, then this would be a negative change in temperature. All right, so let me get out my calculator really quick. Just to get a number, 4186 times 0.5 times 20. And I get, of course, I don't know why I didn't think of it, 4186.0 joules. That's how much energy I would have to add to the water, heating it up, put it over flame or on a stove or whatever, to change the temperature of the water by that amount. Okay, fairly straightforward. Given all the information in the problem, plug the information into your equation and get the answer. Any questions on this particular example?
I have a question.
Mm-hmm.
So C will always be 4,186 joules per kilogram.
If the material we're talking about in the problem is water.
Okay.
If we're dealing with a different material, so let's say you had a metal bar that's made of steel, well, then I'd have to look up what's the specific heat for steel, and maybe that's 500 or some other number. But water specifically is this number always. So each material will have a different number.
Thank you.
I have a question. So you know how
Sure.
in a problem, the temperature of the mass is 5 kilograms. If it was given to us in grams, will we have to convert it?
Yeah. So you're always going to want to use kilograms as your units. So one thing that I can do as a teacher in trying to trick you on a question to make sure you're paying attention is, instead of saying, I want 0.5 kilograms of water, I could have said, I want 500 grams of water. Well, 500 grams, if you convert it to kilograms, is 0.5 kilograms. So yes, always convert to kilograms in these problems, because the units of mass for physics is always going to be kilograms. Yeah, so definitely be careful about that for sure.
I have a question as well.
Yeah.
Where you put CH2O, I can't comprehend the J. Like, what did you write under the joules? I can't.
Sure. That's joules, so capital J. These are just the units. Joules per kilogram, so kg,
Okay.
times Kelvin.
Okay,
Yeah.
thank you.
Yeah.
I have a quick question too.
Sure.
So I know the problem said increase in temperature, but so with the 20 degrees Celsius, like, since it wasn't stated before, that would be like technically the final minus initial, which is the 20 degrees Celsius.
That's right. Yeah. So in this case, I didn't need to write here final minus initial, because I was told the change is 20. Now, another question, what I could have said was, I want to increase the temperature of the water from 30 degrees to 50 degrees, right? And in that case, then I would have said, okay, the final temperature is 50, the initial temperature is 30, and 50 minus 30 is 20. So that is a change in 20, but I didn't know ahead of time the change in temperature. What I knew was, where did I start and where do I want to end, which means the change in temperature. So yeah, this could be, I'm going from 30 to 50, or it could be I'm going from 200 to 220. I don't know what the actual temperatures here are. All I know is whatever it's at, I want to go 20 degrees more. So I have a change of 20. Yeah, but deep down inside of that 20, it meant some final and some initial temperature that's 20 degrees apart. Yeah. Any other questions? All right, well, with that, let's try another example. Very similar. This time I'm going to say you add 50,000 joules of energy to 250 grams of water. If the water was originally at, let's say, 10 degrees Celsius, what will be its final temperature? Okay. So similar question. Here I'm told I have water, a certain amount of water, 250 grams. The water has an initial temperature of 10 degrees Celsius, and I'm going to add 50,000 joules of energy to it. So I'm going to heat it up. And what I'd like to find out is how hot will it get? What will be its final temperature? Okay. So again, I only have one equation to work with. Q equals Cm delta T. That's what I have. Now this time I'm going to go ahead and rewrite it where I say what delta T is. So it's C times M times final minus initial temperature. Okay, so those are all my variables. Q, how much energy did I add? C, what type of material is this? M, how much of the material do I have? Final temperature, which is the thing I want. And then the initial temperature, where did it start? So yet again, let's plug the numbers in that I know from my problem and solve for the unknown. So Q, that's how much energy do I add? I add 50,000. C, that's the specific heat of the material. In this case, it's water, which happens to be 4186. M, the mass, how much water do I have? I'm told I have 250 grams. Now, grams is bad. I don't like those units. What I want is kilograms. And if I convert, 250 grams is the same as 0.25 kilograms. Times final temperature. Well, I don't know what that is, but that's the thing I want. So I'll leave that as a variable. Minus the initial temperature, I know, I'm told I start at 10 degrees. So I'll leave it as 10. Now, you may be changing everything here to Kelvin. So if you wanted to use Kelvin temperatures to plug in here, then instead of 10, you'd be writing 283 because Celsius plus 273, well, it's 10 degrees plus 273 is 283. So if I were going to use Kelvin temperatures, I would say the initial temperature is 283. And what that would do is when I get an answer, the answer will be in Kelvin. Here I'm using Celsius. So what that means is when I get an answer, it's going to be a Celsius temperature. For our stuff, that's perfectly fine. Again, because this is a delta T style of problem, I'm allowed to use Celsius. Now, that's for my class. If you go to chemistry and chemistry says otherwise, don't blame me, follow their rules in their class. In my class, I allow you to do it either way when the equation has delta T. If it doesn't have delta T, then you have to use Kelvin or the numbers are completely wrong. All right, so there we go. There's my equation. I have all the numbers in. I've got one single unknown sitting there. So this I need to solve. So let's try it. First thing I'll do, let me leave the 50,000 alone. I'll go ahead and multiply 4186 times 0.25. So 4186 times 0.25. And this is 1046.5 times final minus initial. Okay. Next step, if I'm going to do this step by step, leave 50,000 alone again. And now what I have to do is I have to multiply that 1046 times each of the two things in that binomial. So I get 1046.5 times TF. And then I have to multiply by the negative 10 minus 10465. Okay. So all I did was I distributed the number times the TF and times the negative 10. And there we go. Again, just algebra. Bring the 10465 over to the other side. So I get 50,000. When I bring it over, it goes from negative to positive. So I'm adding 10465 equals 1046.5 times TF. Okay, so add 50,000 to 10465. So 50 plus 10465, I get 60465 equals this number times TF. And of course, get TF by itself, divide over the number. So 60465 over 1046.5 equals TF. So plug it in my calculator, 1046.5, and I get 57.78 degrees Celsius. Now, before I box this as my final answer on a test, I want to see, does it make sense? Okay, because obviously I could have made a mistake in the algebra. I could have made a mistake in my calculator. Can I look at the answer and tell if it's definitely wrong or could it be right? I can't tell you if it's definitely right, but at least I could see big mistakes. So if we remember what this question said, we're taking some water, it's at 10 degrees, and I'm going to add a bunch of energy to it. So obviously the temperature should go up. Whatever it's going to be, it better be bigger than 10. Now, how much bigger, I don't know. But if I get 3 as the answer, I know I'm wrong. I can't add energy to it and make it get colder. So it should be something bigger than 10. What do I get? 57. That's bigger than 10. So I can't say it's right, but at least I can't say it's definitely wrong. So I could be kind of confident and go ahead and box the answer. If, by the way, question?
Oh, I had a question. Could you also plug that number back into the equation to see if you get 50,000?
Yeah, for sure. That's absolutely possible to do. Go back to the original equation right here and put in for TF 57.78 and calculate that right side and see what number you get. It won't be exactly 50,000 because of rounding and decimals, but it'll be really, really close. And so good. That's a good way to check. Also, for those of you that wanted to do Kelvin instead of Celsius, what you could do is take this number, if you got this number, and add 273 to it. And the answer would be 330.78 Kelvin. So either one of these two answers is fine for me. If I'm grading your test, if you give me 57 degrees or 330 Kelvin, they're both fine. Any questions about this example?
I have a question.
Sure.
So I'm a little confused on how I see how you got the 1046.5 in the parentheses with the final minus 10.
Mhm.
But what did you do on the next step? Like, did you distribute it or something?
Yeah. So going from here to here,
Yeah.
What I did, and I'll do it without the numbers, just so it looks easier. You have some number, that's the 1046.5. And then I'm multiplying it by, let's say, B minus C, right? That's basically what we have there, but with a bunch of numbers. And so all I did was I said, this is the same as A times B minus A times C, right? I distributed the A times the first term and then times the second term. And so what I did, 1046.5 times TF, that's this piece here. And then I did the 1046.5 times negative 10, and that's this term right here. Okay, so A times B minus C is A times B minus A times C. So that's how I went from that step to the next step.
Okay, I understand. Thank you.
Sure, sure. Any other questions? Now, certainly this example was a little bit more of a pain in the butt than the first example. You could just look at the work and see the difference. This took 2 lines and this one took, I don't know, 6 lines or something. And that's because the algebra to get to the unknown was a little bit more complicated. It's not hard. We know how to do the algebra. It's just, it took some more work to do. Fine. You just have to concentrate more and be careful about what you're doing. But it's the same equation, and we're just plugging the numbers into the equation and solving for what we want. Now, one thing you can do, which I can show you, some people like to do physics the way I'm about to show you, and some people like to do physics the way I just did it. And the difference is, do you plug the numbers in first and then solve for the variable, or do you not plug any numbers in at all, solve for the variable first, once you had the final thing solved, then put the numbers in, okay?
I know
Two
an
different ways
easier
to do it.
way to solve for the variable. Like, you know, the step where you have the TF minus the 10. Instead of that, you could have kept that as being the change of T and then divided each side by what 4186 times 0.25 is. So if you divide the 50,000 by 1,046.5,
Mhm.
and then also the number that you get for that would be your change of T. And then all you have to do is do that number multiplied by TF minus 10, add 10 to both sides, and then you can still get your answer. If
That's
that kind of
very-
makes sense.
No, it makes a lot of sense. It's actually
Because
very
it's kind of confusing because it looks like it's another step when you write out the TF minus 10. But if you keep that as the change of T, then people will know, because the equation for the change of T is TF minus T initial.
right. No, you're exactly right. What I could have done, as you said, is stay here with this equation here. Not write out what delta T means yet. Just leave it as delta T. And then solve for what delta T is. And I would get, oh, delta T is 47.78. And then you say, okay, well, if the change is 47, if I start at 10, just add 47 to it. That's exactly right. Now, the reason I didn't do it, however, is because I'm looking ahead at the types of questions we're about to be getting, where you actually have more than one item all at the same time. With that, you can't do it anymore. If the question is purely this question, where you have one thing, you're adding heat or taking heat away, whatever, and it will change temperature, you're exactly right. You could solve for what is the change and then apply the change. Much easier algebra. The reason I went through these steps is because as soon as I add a second item, and now they're going to add energy between themselves, both of them will have a change and their changes will be different. And so I can't just solve for a change anymore. So I'm trying to be careful about doing that, but you're perfectly right. For this question, that would work well. And here's another thing you can do, which is what I was just discussing. Let's say instead of plugging all the numbers in at the beginning. In fact, when I was a student in college, one professor I had demanded we always solve problems the way I'm about to show you. He would never let you plug numbers in first. So what he would say is start with the equation Q equals CM TF minus T naught, right? Final minus initial. He says, don't worry about the numbers. Forget the numbers. Solve for TF here. So I say, okay, well, how would I solve for TF? Well, TF is in this parentheses, right? I can't get it out of the parentheses safely. So let me leave that alone, but the C times M thing, I can move it to the other side. So when I divide it over, it's Q divided by CM, and what's left on the right is the parentheses, TF minus TO. And now I could get rid of the TO, bring the TO to the other side. So I get Q divided by C times M plus TO is equal to TF. Okay, and now what I've done is I've taken my original equation and I've solved for the thing I'm actually looking for in this problem, which is final temperature. At this point, now what I can do is plug all the numbers in. Say, well, the Q, I added 50,000. C, 4186 times M, 0.25. And then all of that plus the initial temperature, which was 10. And if I do that, that'll give me the same answer I got before. And you can see the algebra looks a little easier here. You don't have all the numbers all over the place. All you have is a bunch of variables. And if you're comfortable moving variables around, this is much cleaner. And then once you've solved at the very end of the day for whatever it is you're looking for, then you plug the numbers in.
Yeah, that looked like 100% easier.
Yeah, it is true. And in fact, there's a lot of times where this is a very, very big benefit because things can cancel. In this case, nothing can cancel, but there's a bunch of places where, for instance, if you remember conservation of energy, where you'd have, 1/2 mv squared plus mgh equals, let's say, 1/2 mv final squared. And so let's say I want to solve this for v final, so I divide everything by 1/2 m. Okay, that gets rid of that. And then I'm going to be taking the square root. All right, well, notice there's an m, an m, and an m. All the m's cancel. So I would never have had to put the m number in the equation at all because they would have canceled out at the end of the day. But if I plug everything in up front, I don't know it'll cancel. So there will be times where, because you don't know things will cancel out, you'll be using numbers that are meaningless to you. So this is a very, very powerful technique. I don't always do it because just teaching over a number of years, I almost always see students put numbers in at the beginning and then manipulate numbers. I don't know why. Certainly, if you look at this looks a lot neater and more easy to follow. But I've found a lot of students are more comfortable moving numbers than letters. I will not demand one way or the other. If you like plugging the numbers in at the very beginning and then doing the algebra, that's fine. If you like doing the algebra first and then plugging the numbers in at the very end to get an answer, that's fine too. Know that both techniques exist and they're both powerful. One of the reasons to plug the numbers in at the beginning is, you notice I have C times M, 4186 times 0.25. Well, I multiply it and it becomes one number now. So now it's not C times M, it's just a number. And so now I'm just moving that one number around. Whereas over here, it still looks like it's two different things. Granted, I'm moving it as one object, C times M. So in my mind, it's still one thing. But when I'm plugging the numbers in at the end, it's still two different objects. So there are pros and cons to both techniques. And what I would suggest for you is, when you're practicing some of these problems, try out both techniques, see which one is easier for you to follow. Which one will you make less mistakes, and just do that. They're both fine. All right, so any questions about this particular example? All right, now we will do an example that's a little bit more complicated. Here we will mix a couple of different materials together. So with this example, we'll say you have 1 kilogram of hot coffee at, let's say, 90 degrees Celsius. You wish to cool it down to 70 degrees Celsius using milk, which starts at 5 degrees Celsius. Okay. So you have a cup of hot coffee. You know the temperature of the coffee. You know how much you have. You have some milk in the fridge. You're going to take it out of the fridge and you're going to pour it into the coffee until everything equilibrates to 70 degrees. And you'd like to know how much milk should you be adding. Okay, so how much milk should you add? Now, in order to do this, let me give you some pieces of information. Let the specific heat of coffee be the same as for water, so we'll call it 4186. And let the specific heat for milk be, let's say, 2000. All right, so there's our question. How do we solve something like this? Now we have multiple things in our system. And what we'd like to find out is how much milk. So the mass of the milk is what we want. What we're going to do is use conservation of energy. Okay. What I'm going to say is this. Think about, you have a closed system. So I don't know, you have an ice chest or something. You put objects in this thing and energy is not allowed to escape and you can't feed energy in. So it's closed off. All the energy remains in this thing. And I put 2 objects here, object 1 and object 2. Okay, let object 1 be hot and object 2 be cold. What's going to happen? Well, obviously, the hot guy will heat up the colder guy. He will lose energy because he's got a whole lot of energy. He's got too much. The other guy doesn't have enough energy. So he's going to feed energy to this second object. And he's going to keep feeding it, raising the temperature of 2, lowering the temperature of 1 until they're at the same temperature. Once they're at the same temperature, then there's no reason to move energy back and forth because they're at the same temperature. Neither one is hotter than the other. So if that's how things work, which is how it works, then what we could say is whatever energy, whatever Q, 1 gives away, object 2 has to take it in because it has to go somewhere. Object 1 is giving away its energy, but the energy can't leave. It can't leave the system because it's in this box. So the only place it can go is to 2. So if I add the amount of heat that object 1 loses and the amount of heat object 2 gains, they better be the same number. So it better equal 0. Because object 1, in losing energy, that's going to be a negative number. So he loses 100 joules. But object 2, all he can do is gain 100 joules. He can't get more than that. There's no other energy there. And he can't get less because that 100 joules has to go somewhere. So whatever 2 gains, 1 must have lost. So this is conservation of energy. There's some energy in the system. It can't change. If 1 loses it, 2 has to gain it. There's no other choice. So that's our big equation. Question?
Yeah, so would 1 always be negative and 2 always be positive?
Only in this example where I've stated that 1 is the hot thing and 2 is the cold thing. It could be that 2 was the hot thing and 1 was the cold thing, in which case 2 would be the negative guy. But then you could just call 2 1 because it's just a name. Who cares what you name it? But in all of these things, every question we're about to do, there must be something that's hotter and something that's colder. So there will always be something that will lose the energy and something else that will gain it. Because if it didn't happen, then that would mean everything's at the same temperature. So nothing would change temperature. So there will always be something we could call the negative one, and something else will be the positive one. Or we could have 10 objects where maybe one of the objects loses energy and 9 of them gain it, or some combination. So, excuse me. So you don't have to worry which is the negative or the positive, because when you plug numbers in, it'll come out for you. You don't have to think about it. But this thought process is what allows us to create the equation we're going to use. So if this is what we're going to say, another way of saying it is the amount of Q, the amount of heat gained, plus the amount of heat lost is equal to 0. That means the same thing. 1 gained energy, 1 lost energy. Then all we have to do is replace Q. We don't know what Q is. I have no idea how much energy is going to be lost. But what I do know is whatever that Q number is, it's the same as Cm delta T for number 1 plus Cm delta T for number 2. Right? Each Q is Cm delta T. So object 1 has his Cm delta T, object 2 has his Cm delta T. And if there's more objects, then there's a 3 and a 4 and a 5 and whatever. If you add all of those Cm delta T's up, it's going to add up to 0 because some are going to be negative, some are positive. And they'll always equalize. That will be our final equation. That will be the thing with all the variables in it where we plug our numbers in. Okay, so that's what we're going to do for this question. So let's try it out. In this case, we're going to say we have Q for the coffee. So that's how much heat the coffee is going to give away because it's too hot. It's going to lose energy to the milk. How much? This much. Plus, the milk will gain some amount of energy in heating up to its final temperature. Those are the only 2 things in my problem. I've got hot coffee and I'm putting cold milk into it. So just 2 objects. So Q for the coffee, Q for the milk. Set it equal to 0. From here, what is Q? Well, C for coffee, M for coffee, final minus initial temperature for coffee. So all of this is for the coffee. And then C for milk, mass of milk, final minus initial temperature for the milk. Those 2 things added together give you 0. And now we have our final equation. We're going to know every piece of information here. And there's going to be 1 unknown. What's the unknown we're looking for? How much milk, that is the mass of the milk. So there's our unknown sitting there. Every other variable in this problem, we know the answer to. So let's plug the numbers in. All right, specific heat for the coffee, I was told in the problem, use 4186. So 4186. The mass of the coffee, how much coffee did I have? 1 kilogram. So 1. Then I have the coffee final temperature. Well, what I want is to add enough milk such that the coffee goes down to 70 degrees. So his final temperature should be 70, and he started at 90, I believe, right? Yeah, 90. So there's all the information about the coffee. And now I do the milk. Plus specific heat for milk, I was told in the problem, use 2000. The mass of the milk, I don't know, but that's the thing I want. So I'll leave it as a variable. And then we have final minus initial temperature of the milk. Well, because I know when I stick the milk in the coffee and I stir it around and I wait, if the coffee got down to 70, the milk had to heat up to 70 as well. Everything goes to the same final temperature. That's what equilibrium means. If everything is in equilibrium, they all have the same final temperature. So the milk's final temperature is also 70. However, his initial was 5. He started really cold. So there's the stuff for the milk. And again, coffee plus milk equals 0. And now you see the equation I have to solve. One unknown sitting there, everything else is a bunch of numbers. So let's try it. Let me do, first of all, 70 minus 90 is negative 20. So 4186 times negative 20 gives me minus 83720. So all those numbers on the left equal this. And notice it's negative. Just like I said, the hot guy is going to lose energy, so his stuff is going to be negative. And now we look at the milk. Well, let me leave the M alone. Obviously, I can't do anything with him. The other numbers, though, 70 minus 5 is just 65, right? So I have 2,000 times 65 gives me 130,000. And that's equal to 0. This is a lot cleaner, a lot more easy to see how to solve for M here. I want to bring the 83,720 over. So I have M times 130,000 equals 83,720. Divide over the 130. 83,720 over 130,000. Plug this in my calculator. Let's see, 83,720 over 130,000. And I get 0.644 kilograms. So how much milk should I add? About half a kilogram, 0.6 kilograms of milk. If I add just that amount of milk, then, and I stir everything around and let it sit and get to equilibrium, then everything will be at 70 degrees. I'll be able to drink my coffee without burning my tongue or whatever the case may be. And so there we go. A fairly complex, seemingly complicated question. I have a certain amount of coffee, which is at one temperature. I want to add this other thing that's made of something else, which starts at a different temperature. I want to add and combine everything together and get to some final temperature. How much of that milk should I add? Turns out it's really not that hard to calculate. First thing I do is I say, okay, for my system, what are all the things which are important? That means what are all the things I could change temperature? So for me, there's only two things. The coffee can cool down and the milk can heat up. There's nothing else here. So I'm going to have a Q for the coffee and I'm going to have a Q for the milk. Since I don't know what Q is, I don't know the number for Q, I replace Q with what Q equals, which is Cm delta T. So now I have Cm delta T for coffee plus Cm delta T for milk equal to 0. At that point, I look in my question, I get all the numbers, all the data from my question, and I plug all the numbers in. One of the terms in my equation will be the unknown. In this case, it happens to be the mass of the milk. There could be another question where if I add 0.75 kilograms of milk, what will be the final temperature? Well, now I'm solving for final temperature instead. But in this case, I wanted the mass of the milk, so that's my unknown. Everything else is a bunch of numbers. At that point, it's the algebra. Calculate all the numbers, manipulate the equation, move things around to get your unknown. Any questions about this example? All right. Well, unfortunately, golly, it's already the end of the class. I don't know. I think we only did 2 or 3 examples. But this is going to be this part of calorimetry. There's a second half, which we're going to get to next time. And that second half, I'll foreshadow it a little bit here, deals with, well, what if the object that you put in, so let's say I like to cool down my coffee because I'm very sensitive on my tongue. I don't want to burn myself, but I don't like milk in my coffee. I just want black coffee. So maybe I want to add an ice cube to it to cool it down. Well, if I add an ice cube, something interesting happens. Not only are you changing the temperatures, but the ice changes phase. It melts. It goes from being solid ice to liquid ice. Now, that may not be important. There could be some universe out there, well, who gives a crap if the ice went from solid to liquid? But in our universe, it matters. And it matters because not only does it take energy to change the temperature of something, but it also takes the energy, to change the phase, the state of matter. So just making it go from solid to liquid, even if you don't change temperature, if it's at 0 degrees and it goes from ice to water because it melted and it's still at 0, well, Cm delta T would say no energy. But we know from actual experiments, there's a lot of energy it takes to do that. So right now, we don't have enough stuff in our equation to take that stuff into account. What that is called is latent heat. Just like specific heat is how much energy to change temperature, there's something else called latent heat, which is how much energy to change the state of matter. Okay, so what we're going to learn for the next piece of this is, what if we start plugging in stuff where it can melt or it can boil or something like that? How do we take that stuff into account? It's still going to be just like this. It's just maybe there's some new Q over here. Q for the ice and Q to melt the ice or whatever. Just more pieces that we plug into this equation. Some will be Cm delta T, some will be this other thing. So it doesn't complicate it much, but it does add to it. Next time we'll do some more examples because obviously this was the first kind of complicated type. We'll do another one that has multiple pieces in it, and then we'll start talking about latent heat. So that's all I have for today. I did post on Canvas last year's lectures on calorimetry and example lectures as well as the practice problems and solutions. So it's all there. You don't have to worry about latent heat stuff yet because we haven't gotten to it, but at least those practice problems that are like this, which are just Cm delta T, you can start working on that kind of stuff, which I would recommend you do. And then if you have any questions about them next time we meet, you can ask specific questions on that. But we'll continue with this topic next time. So with that said, if you have no questions, you are free to go, and I will see you Friday.
See you Friday.
Thank you.
See you later.
I do have a question.
What's up?
So throughout the lecture, my phone has disconnected me from Zoom, so I've missed pieces of the lecture. I saw that you're recording. Is there a way for me to look back at the recording later?
Yeah. In fact, each of these is recorded, and Zoom is taking care of that for me. I'll download them and start feeding them into Canvas. But in the meantime, until this specific thing is up there, on Canvas are the ones that I did last year, which is the same stuff. except of course, maybe I did a different example or something. So until that's posted, or until this one's posted, you can look on Canvas at the ones we did last year and start getting that information from there as well. It's the same information. It's just, it's what I did last year.
Different example. Okay.
But yeah, for
Thank you
sure.
so much. I appreciate it.
Sure. See you later.
Okay, bye.
Bye.
Uh,